Next up is the section on building envelope, which means specifying the areas of the district through which the buildings will lose or gain heat. This is of course important because it directly influences the heat demand and the cooling demand that the district will have, depending on the size of the external areas and its heat transfer coefficient, which we sometimes call U values. So here we need to specify all the areas that separate a conditioned space of a district, so all kinds of rooms, to the outdoor environment through which they will lose heat. So this is typically all the external walls of facades. This includes windows here, so this is the gross external wall area, which need to be supplied here. The roofs areas and the ground floor. And for each of them, there is also a heat transfer coefficient provided. These heat transfer coefficients are passive house grade U values, which means that they have a very high level of insulation and lose very little heat in winter. Now, for modeling existing buildings, these values will definitely be too high, and you might need to check literature or your project specifications to obtain more realistic U values. But in terms of a optimal district that has a state-of-the-art thermal hull, these values are applicable. Once you have added the rough areas of your building envelope, next thing is to specify a little more in detail the geometry orientation, which means the distribution of how many of your vertical walls, meaning your facades, face each direction, north, east, south, and west. If they are relatively homogeneous buildings, then they might be equally distributed between all orientations. But sometimes buildings have a predominant orientation that is facing in two opposite directions, east-west, for example, facing the buildings, or north-south facing buildings. For each of these orientations, you also have the option, or actually the requirement, to specify how much of the external walls are occupied by windows. This is again a gross estimation, so 40% means 40% of the gross area here will be assumed to be windows, including window frames. There is a default ratio for window frame to window pane value applied here also. Now these are important because they influence how much solar radiation is getting into the building through the windows. So typically north-facing facades might have a different or a smaller fenestration rate than south-facing windows, and you can also try and change these values and see what the effect on the energy balance is. Now, sometimes it's not as simple as that. Typically, many buildings have many more orientations than just these four. So it is important to keep in mind that this, of course, being an Excel-based solution, is a relatively simplified model. All we're doing here is using the weather data that is provided, which is now currently the Viennese weather data, and taking the orientation, the irradiation that surfaces of different orientations receive, and taking this into consideration when calculating the solar gains of the building. So this means that if you have walls that lie between north and east, for example, exactly that center is exactly northeast, so it's equally as far away from north and east, then you can just split it up between the north and the east orientation, and half of the building windows will receive the north-facing irradiation and half will receive the east-facing irradiation, averaging to a northeast orientation. This way you can approximate almost all orientation with sufficient accuracy. Another important aspect is on the thermal hull. Typically, buildings are more complex than just having these three surfaces. What is important here is to keep in mind that we are not modeling the building geometry per se, we are modeling the thermal hull of the building. So meaning the surface of the building that encloses the building and where the heat transfer, the heat loss is most prominent, which is typically the external walls. And for roofs, it sometimes is more difficult. For example, in existing buildings, in old buildings, you might have a attic, which is unheated, and above that you have a tiled roof, which does not have any significant insulating value. So the thermal hull of the building, where the difference between outdoor temperature and indoor temperature is most prominent, is actually the uppermost ceiling of the building, so the ceiling leading to the attic. And the attic is actually already considered outdoor temperature. There are some ways to model this by reducing the U value of the corresponding thermal hull element by a factor of 50 or 60 or 70, 80% to reflect this buffering effect of the outside. You can read up on this in the literature. Just keep in mind that we're not modeling the building geometry, but rather the areas of the thermal hull of the buildings.